on and proceed, but basically I want to do a sample problem at least of each type. So we start moving down in order, power series solutions. And unless somebody really wants one of the others, I'll do the one from last year's exam. So second derivative minus xy prime plus 2y 0. In particular, the kind of statement here, wait. I'm sorry, but voices carry from the back of the room. You're at the narrow end of the megaphone, and that's why you speak into the narrow end, is so that your voice is amplified at the other end. So power series solutions, and we have, be sure to give the recurrence relation, indicate the two linearly independent solutions, and at least the first 6 non-zero terms. Okay, so the idea here is that we look for a solution of the form of a power series a sub n x to the n, derivative. In particular, when this of course is a0, a1 x, a2 x squared, and so on, so that when I take the derivative, the constant term goes away, the index drops to 1. Derivative of a sub n x to the n is n a sub n x to the n minus 1. Second derivative, again, the constant term now is the n equal 1 term, the n 1 times a1 x to the 0 is 1, so I lose another term, n minus 1, a sub n x to the n minus 2. And the power series solution is basically a one idea and execute thing. We have this form for the solution. Substitute in and see what happens. 2 to infinity, n minus 1, a sub n x n minus 2, minus. The most common error that I have seen over the years in grading power series problems is to leave the x outside the sum. Okay, that x needs to move inside the sum, so I have x times the series for the derivative. The terms in here, n a sub n x to the n minus 1, x to the n minus 1 times x is x to the n. Important thing, if you find yourself with a recurrence relation, the relation between the a's, which involves x, you've made that mistake. You haven't brought a factor of x in. Those things can be constants. They have to be constants. They are functions of n, of the index, but that's the only thing that can vary in there. And then the function term has a sum 2 a sub n x to the n, 0 to infinity. Okay. And now what I need to do is get all of these things to have x to power that looks the same, so that I can combine these things. I've got x to the n on these two terms. I'm simply going to, I want all of them to be in terms of x to the k. So I'm going to replace in these two series n by k. That doesn't require anything more than rewriting it. K a sub k x to the k, k equals 0, infinity 2 a sub k x to the k. Leave out the 0. But on this term, I want the exponent. I want the exponent on x to be the same in every series. So I want k to be whatever is in the exponent. In this case, n minus 2. I have to be consistent there. So n is k plus 2. And change it everywhere. When n is 2, k is 0. K plus 2, k plus 1, a k plus 2, x to the k. And now I look at this and see, can I combine everything into one thing, into one series? And I look here and say, this one starts at 0, but this one starts at 1. The first series has one more term, the k equals 0 term, than the second series. The third series also has a k equals 0 term. So I write those two terms separately. The k equals 0 term here is 2 times 1, a2, x to the 0. There's a k equals 0 term in the second one, so this is a 2a0. Where's my separate color? So these are the k equals 0 terms. And then everything from k equal 1 on, everything has a something times x to the k. The first one has k plus 2, k plus 1, a sub k plus 2. And then the next one has a negative k times a sub k. And the last one has a plus 2 times a sub k. I can combine those into a single term, like so. And so now I have the relationship that this has to be, every term in this sum has to be 0. And so for this sum to be the 0 function, the coefficient of every power of x has to be 0. And so I get k plus 2, k plus 1, a k plus 2, plus 2 minus k, a sub k, equals 0. And this is valid for values of k that start at 1, yeah. And this is basically my recurrence relationship. I choose to rewrite it in the form a k plus 2. I'm going to move this to the other side by writing this as k minus 2, k plus 2, k plus 1, a sub k. This is the recurrence. I put a box around that so the grader can find it and give me credit. Right? That's part of that's the game, right? To go and get the things there. So A0 and A1 are starting places. The k equals 0 term gives me that A2 is negative A0. From k equal 1 now. From k equal 1, I get that A3 is 1 minus 2, negative 1, over 3 times 2, A1. Question here? K equal 2 says A4 is 0 over 4 times 3, A2, that's 0. K equal 3, A5, 1 over 5 times 4, A3, but here's A3 right above it, so that's a negative 1 over 5 factorial A1. How many terms do I need? I need 6. I start to wrap this up by writing down a solution. I have A0 times 1, A1 times X. The coefficient, all the things which involve A0 are going to give me one of the linearly independent solutions. Everything involving A1 is the other one. So the next thing here is A2. A2 is negative A0. That multiplies X squared. A3 is negative 1 over 3 factorial X cubed. A4 seems to be 0. A5 has a negative 1 over 5 factorial X to the 5th. 1, 2, 3, 4, 5. The statement of the problem asked for 6. I need one more. So K equal 4 is going to give me K equal 4 is A6 is 2 over 6 times 5, A4, but A4 is 0. In fact, all the even ones after A sub 2 are 0. K equal 5 gives A7 as up there 5 over 7, 6, A5. 5 over 7 factorial A1. Oh, there it is. There's a negative sign there of that. Negative 5, 7 factorial X to the 7. And so I have a solution, one linearly independent solution, in fact a polynomial, plus the other one. Professor Levine likes power series problems where one of the solutions is a polynomial. I think you had one was on this exam, the last one? No. Yes, sir, Tommaso.
Oh, so you prefer to just go from the 0 indice to 1, but we could have went the middle one from 1 to 0, correct?
You're always going. You start out A0, A1. That's a given. And the question then is to go down the list to generate A2, A3, A4.
I'm saying up here, when you chose to make like indices,
right?
You transferred the 0, 1 on the ends to 1. You could have went the middle one down to 0 if you wanted.
No, because there's no 0 term there. Oh, you're saying because this is 0.
You could have made that K equal
I could have made
0.
that 0 only because this
the
is
0 term
there's a
is
0 term.
You
Yes.
just would have added 0.
Yes.
It would have been a little easier.
Maybe.
Right? For me it was.
Okay. Whatever works. Patrick?
Is the 8 to the 7 term correct? Should it be 3 over?
Is the A, no, it's 3. Thank you. That looks like a better pattern. The next one's going to be 5. So eigenvalues, eigenfunctions.
Do we have to write it as like that, or can we just list them? Can we do like A1,
You are-
A0, A1, A2, A3, A4?
The question for the back of the room is, why did I write it this way? The instructions on this problem say indicate the 2 linearly independent solutions. If I just wrote, if I just listed them all in order, that doesn't pick out the 2 linearly independent solutions, okay? So I was looking for those, and therefore A0, everything involving A0, that's one of my linearly independent solutions. A1, everything involving A1, that's the other linearly independent solution. So the 2013 exam specifically asked for that. The other 2 did not. And so then I could have just listed them as they came. Okay? So So it is a matter, read the exam, see what you're specifically being asked for.
What's the front of it?
Eigenvalues, eigenfunctions. 2013 and the one, we didn't teach the course in 2011, Professor Levine and I. He wasn't teaching, I taught something else. If you look at that, it was Cauchy-Euler there. Well, we inflicted that on you on Wednesday. Once is enough. And incidentally, one other thing, if you look at the problem, on the other hand, from the 2010 exam, and actually take the derivative of the first term, it's xy double prime plus y prime plus lambda over x, y equals 0, and multiply through by x. So the problem on the 2010 exam and the one on the 2013 exam, in fact, were exactly the same problem.
Wow.
Another reason that I advise you to look at past exams, sometimes problems from a couple of years ago come back.
So we're not gonna have eigenvalues, right? Or we're not gonna have Cauchy-Euler, right?
You're not going to have Cauchy-Euler. You had Cauchy-Euler, yes. Once a semester is enough. So I'm going to do the other one. I'm going to do the one from 2012. And so here, y double prime 2y minus lambda y equals 0. Y prime at 0. Is y prime at pi equals 0. Right, information like that is the reason you come to the review, and the people who aren't here don't know that, right? Okay, so So I start out here, it's constant coefficients. I write down the initial equation, r squared plus 2 minus lambda equals 0. R squared is lambda minus 2. R plus or minus square root of lambda minus 2. And so here you're asked to look at the three cases. The three cases are always based on the quantity under the square root, the so-called discriminant for the quadratic equation. In this case, that quantity is lambda minus 2. So we want to see what happens when lambda minus 2 is positive, 0, or negative. And that's the order in which I always do these things. Whatever's under the square root, positive first, then 0, then lambda, because I know positive's probably not going to give me anything. 0 maybe, and especially when there's derivatives involved, 0 probably. Certainly there's a likelihood there. The negative one, the sines and cosines, pretty much always. So here, case 1 is lambda minus 2 positive. And I like to write then that quantity, just moving along the Greek alphabet from L to M, lambda to mu, write it as mu squared, and so R is plus or minus square root of mu squared, plus or minus mu. The solution C1 e to the mu x plus C2 e to the negative mu x. The boundary conditions are given in terms of the derivative. So I'll calculate the derivative right away. Mu C1 e to the mu x minus C2 e to the negative mu x. At 0, I have mu e to the 0 is 1, so that's C1 minus C2. And therefore C1 equals C2. Y prime at pi. And I'm going to put C1 equals C2 in this thing. Mu C1 e to the mu pi minus e to the negative mu pi. I know that mu is not zero, pi isn't zero, so the exponential function is a strictly increasing function. It's at a negative and a positive value, same negative and positive value, the exponential can't be equal, and so C1 is 0 and C2 is 0, and the objective of the eigenvalue problem is always to find non-zero solutions which satisfy the equation. Clearly, y equals 0 satisfies everything, and therefore we can immediately observe that, and it's no longer of any interest. Okay, so case 2 then is the 0 case, lambda minus 2 equals 0. The differential equation is then y double prime equals 0. The solution C1 plus C2x. The derivative, again, the boundary condition in terms of the derivative, so the derivative is C2. Y prime at 0 is C2, that's 0, that's the same as y prime at pi. So I have no restraints on C1, and therefore I conclude that lambda minus 2 equals 0, or lambda equal 2 is an eigenvalue. I'm going to label it lambda 0 now. And the corresponding eigenfunction, there was only the constraint that C2 had to be 0, so y equal a constant. Y equal a constant, any constant other than 0 is a solution. So y0 equals C0, not 0, is my corresponding eigenfunction. So the third case, I've looked at positive and 0, so the third case is lambda minus 2 negative. I normally write lambda minus 2 equal negative mu squared. I know Professor Levine likes to use beta, but we each are old enough to have fallen into habits. And I'm simply, as I said before, merely moved down one letter in the alphabet, whether it be the Greek or the Latin one. So lambda minus 2 is mu squared. The solution to the characteristic equation up there, r equal plus or minus the square root of lambda minus 2. So that's negative mu squared plus or minus mu pi. So solution C1 cosine mu x plus C2 sine mu x. The boundary conditions, which whether by design or accident are nicely placed just above where I am. In terms of the derivatives, so I'll calculate the derivative. A factor of mu comes out of each of these when I do that. Negative C1 sine mu x plus C2 cosine mu x is the derivative. Y prime at 0 is mu. Sine of 0 is 0, cosine is 1. Mu can't be 0. I'm dealing not with lambda minus 2 equals 0, but negative. So mu's not 0. I might as well assume it's positive, because the negative case is buried in there anyway. So C2 is 0. And then y prime at pi. Let's see, what have I got left here in y prime? There's a mu, a negative C1, sine of mu pi. The C2 was 0. So mu isn't 0. My goal, as I said before, is to find non-zero solutions. So C1, the objective here is to manage this without turning C1 into 0. So that says then for a non-zero solution, I want sine of mu pi to be 0. Well, the sine of something is 0 if that's a multiple of pi. So mu pi is n pi, 1, 2, and so on. Or mu sub n is n. Lambda, and remember, lambda is what the whole thing is about. Lambda minus 2 is negative mu squared. So lambda n is 2 minus mu sub n. More eigenvalues. Corresponding functions. Here's the solution, here's the y. C2 was the thing that became a 0 here, so that got rid of the sine. The solution function that's left is the cosine. So it's the cosine of n pi. And because there's no reason to assume that the constant is the same for each value of n, I can label that C sub n. So these are eigenfunctions.
Would that be n pi x?
Isn't the pi supposed to be x?
Pi is supposed to be x, yeah. I would have gotten there in a minute, thank you. So we've got that. And in summary, eigenvalues are lambda equal 2 minus n squared. Now n equal 1, 2, 3, that's the selection, that's the collection I just came up with. There's also the one over there. It's in exactly the same form. So I can combine everything into one term if I wanted to. And y sub n is c sub n cosine of n x. Again, n 0, 1, 2, and so on. And in fact, setting n equals 0 gives me the C0 that I had identified before. So we get that selection of eigenvalues and eigenfunctions. Okay, get rid of a few bodies, the room won't be so warm. Fourier series.
The fun stuff.
Fourier series. Let's see, what have I shown you here? I've shown you the problems from